We're continuing with section 15.6, change of variables. Now we want to revisit example 1 and see if we can finish up the example 1 using the same, using the change of variable for double integral. So then the story over there was that we're choosing g of r and theta to be x and y, which is r cosine theta and r sine theta. Now let's find the Jacobian. Jacobian of g is going to be either you can write it as this. That's just the notation. It doesn't tell you how the act is being happening, but this one is this tells you a lot more information if you write it as the determinant. So it's the determinant of, this is x, and so x with respect to r, then x with respect to theta, and it's partial y with respect to r, y with respect to theta, those partials. And now this is going to be x with respect to r is basically going to be cosine theta. X with respect to theta is going to be negative r sine theta. And then y with respect to r is going to be sine theta. Y with respect to theta is going to be r cosine theta. This times that minus this times that. That's the story of the determinant. So it would be r cosine squared theta, then minus this times that, which is minus times minus, plus r sine squared theta. Now if I factor r, I end up with cosine squared theta plus sine squared theta inside the factor, and that gives me r. So Jacobian is equal to r, and r is a positive value, so that is going to be our scaling factor. Now let's try to integrate on the simple region E and see how this works. Now let's set up the integral. Two steps of setting up the integral. First of all, you have to match the bounds of r and theta, because on this side, on pre-image side, you have r and theta. So let's set those bounds up. And since it's rectangular, I can change the order without a whole lot of trouble. So I'm just setting up some way. And r runs from 1 to 2, if we remember well, and theta runs from negative pi half to pi. Put the Jacobian in right there. And then the next part is to convert that into function of u and v, because x is a function of u and v, and r and theta, and y is a function of r and theta. So convert that part and then bring it over here. So converting that with using this formula gives me r squared cosine squared theta and r sine theta. So I will have r to power 3 multiplied by the r of the Jacobian, and then I will have sine theta cosine squared theta, and I have to take this integral. Taking this integral, remember there is r to the 4th, one for Jacobian and one for part of the function. these are multiplied by a function of theta. So I can separate things. I can put negative pi half to pi, cosine to power 2 theta, sine theta, d theta, then multiply it by 1 to 2 r to the 4 dr. This part will give me r to the 5 divided by 5, 1 to 2. And this part is going to be a u substitution. What u is going to be cosine theta, du is negative sine theta, d theta, and you see that here is going to be negative du, and here is going to be u squared, and then we figure out from there, and the bounds are going to be cosine at negative pi half, which is 0, and cosine at pi, which is negative 1. So this is going to convert to negative 0, so negative 1. U to power 2 du, which is going to be equal to u to power 3 divided by 3, and negative 1 to 0, which is going to be 1/3. And so 1/3 from here, and over there is going to be 32 minus 1/5, or 31/5, and we add them together and we get the value that we want. Oh, sorry, I meant to say that we multiply it together and we get 31/15. So this part is 31/5, this part is 1/3. The answer to this question is going to be equal to 31/15. We're continuing with section 15.6, and this is change of variables, where this example is asking us, let R be trapezoidal region with vertices 1 and 0. So 1 and 0, and then 2 and 0, 1 and 0, 2 and 0, and then 0 and negative 2, and 0 and negative 1, 0, negative 2, 0, negative 1. And so this is the trapezoidal region. And if you look at it, it's giving you in that order. So this is the region. The region is not too bad, but not too simple neither. It's just it's obviously not a simple region, either in X direction or in Y direction. But it can be divided into two simple regions. But then it's asking us to take the double integral over this region, so this is R, of e to the power x plus y over x minus y. And in either direction, starting with dx or dy that you start, you realize that this is going to be a very complicated integral. It actually is doesn't have an elementary antiderivative, so we are going to look for other methods of solving it. When you set up this equations, you realize a little bit more of an information in there. So things that I notice is, one, I realize that this line is basically x minus y equal to 2. And this line is x minus y equal to 1. And this piece, and then there is a limit in x and y. So in here, x runs from 0 and ends to 1. Here, x runs between 0 and 2. And the direction that is giving, it's actually the opposite. So sorry, this is not. So x runs between 0 and 2. Now, the next question is, how can I make this so I can find the antiderivative, right? The reason you can't find the antiderivative in an elementary form is because here, when I'm taking derivative with respect to x or y, both numerator and the denominator of the exponential are going to of the function inside the exponential contain x and contain y, and so that's the reason. If I'm taking antiderivative with respect to x, I have x on top and I have x on the bottom inside the exponential, and same thing for y. So what can we do? Can we somehow get rid of having the same variable both on top and bottom for the exponential? So the first thing that comes in mind is, let's say if I make this a variable u and make this one a variable v, would that help me a little bit? And so we go and we go into finding, basically, this is what we're saying. We're saying u is equal to x plus y and v is equal to x minus y, right? So when we're trying to find g, I have to find g of u and v equal to x and y. Here is the other way around. And to find g, see, this is basically g inverse. And to find g, I have to solve for x and I have to solve for y. If I add this equation and this equation together, I get 2x is equal to u plus v. So x is equal to u plus v divided by 2. This is the part that I'm trying to find g. If I subtract the 1 minus 2, then I get 2y equal to u minus v. So y is equal to u minus v divided by 2. And therefore my g of u and v, which is x and y, right, is equal to u plus v divided by 2 and u minus v divided by 2. So I found my g. The steps are use that g to find the pre-image of R. So I'm going to erase and put the g on top because we found g, and then I find the pre-image of the region R, call it E or whatever, and then setting up the bounds of integral, finding Jacobian, and setting up the bounds of integral. Now let's find the pre-image of the region R. Let's start with this boundary. Boundary 1 is y equal to 0 and x is between 1 and 2. If I plug it into here, I get y equal to 0. In here I get 0, 0, and so it would be x plus 0 and x minus 0. U is 0 is x, v is x, therefore u is equal to v. So the equation I get in uv plane is u equal to v, and since x is running from 1 to 2, u is going to be running from 1 to 2. And so that gives me the a pre-image of 1, which is the line u equal to v. Now, the second boundary is this one. And the second boundary we decided was x minus y equal to 2. And x runs again between, it starts at 2, goes all the way to 0. Now, this means if I go back to the inverse function, I see that means that v is equal to 2. V is equal to 2, and u runs and so I'm kind of thinking if it 1 and 2 are connected at what u is equal to 2, so it has to be 2 over here somehow also. But how do I find the other side? Or how do I know it's less than, bigger than, and what? Now, if I'm looking at here, this is u and v. If I add u plus v and divide by 2, I get x, right? And x is running between 2 and 0. And v is 2 for good. So if this is between 2 and 0, and then I can multiply both sides by 2, subtract a 2, which is going to get me 2 and a negative 2 on the sides. So I get 2 and negative 2. Then if I want to find the third boundary, the third boundary is x equal to 0 and y runs between negative 2 and 1, negative 1. And again, if I put this in here, I'll see that if I put this in here and I see that y equal to x equal to 0 gives me basically it gives me u is equal to y and v equal to negative y. Therefore, u equal to negative v, u or v equal to negative u. And then kind of starting to think that because I ended at negative 2, now u has to be bigger than negative 2, and then ends up at somewhere else also. And so when I'm looking at that, I realize that again I have to do the same song and dance over here, and I realize that u is actually equal to y, so this is going to be less than equal to negative 1. And so I found a bunch of them. The last one is number 4, and when I'm trying number 4, I see that 4 is what? 4 is x minus y equal to 1, and x runs between 0 and 1. That means that, again, over here, if I look, x minus 1, that's v equal to 1. So v equal to 1. And then I can just imagine that u has to run from negative 1, and then it has to be connected back to the first point here, and 1. But I can also try it. And so how do I know where u runs to? and I'm looking at u over here again. U if v is equal to 1, and so u plus 1/2 is basically is x, and this runs between 0 and 1, and if I solve, I get the same value that I got over here. And so these are the bounds. This is kind of lengthy for finding the previous bound. I can graph this and see the basically how we ended up over here. So I can graph this, and so the first part is u equal to v, but u only runs from 1 to 2, so it's like a little piece over here, and then the second part is v equal to 2, and u runs from -2 to 2, so it goes like that. And then the third part is u equal to -v, but it runs between -2 and 0, so if I dot dot dot, that's a piece. And the last part is v equal to 1, and u runs, so it looks like this. Was there any easier way to do all this process? Let's think about this. I'm looking at these 4 points and I'm comparing them to these 4 points. Let me draw another color. Here, 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 here. This point is 1 and 0. Let's plug in 1 and 0 into G inverse, and I get point 1 and 1, and that's this point. Then let's plug in 2 and 0 into here, and you get 2 and 2, which is this point. Then plug in this point, which is 0 and -2 into here, and you get, if you plug in 0 and -2, you will get 0 plus -2, which is -2, and 2. So that is this point, -2 and 2. If you plug in this one, which is -0 and -1, you will get -1 and 1. Oh, it seems like each corners are corresponding to corners of the pre-image. Is this always true? It's actually true because for this situation, because the transformation that we use, G is a linear transformation. Look at this, it's 1/2 of u plus 1/2 of v for x, and 1/2 of u minus 1/2 of v for y. And linear transformations, again, it's true because it's a linear transformation, linear transformation preserve lines. Otherwise, the corners would match, but we wouldn't know if there are lines that connecting them in between. Here, the reason that you know that you can just find the corners by using G inverse, and then connect them with lines is because there's a linear transformation. Linear transformations preserve lines, and their inverses preserve lines as well. So now that we have the transformation, we have the region that it creates, let's try to find the Jacobian in there and then start integrating. So I'm going to get rid of this piece and this piece, and then I keep and then I start integrating. Okay. Now let's first find the Jacobian of G, and G of u and v, and that's the x with respect to u, x with respect to v, y with respect to u, y with respect to v, and that gives me 1/2 for the first one, 1/2 for the second one, 1/2 for the third one, and negative 1/2 for the fourth one. And then when you multiply this together, you see that the answer is going to be negative 1/4 minus 1/4, which is negative 1/2. So that's a Jacobian. So the scaling factor, has to be 1/2. Now that we have the Jacobian, scaling factor, and etc., let's try to set up the integral. I see that there's one way that I can use to make this be a simple region, and that's if the inner variable is in direction u, and therefore I have to take the antiderivative with respect to u first, and u runs from negative v to v, and v runs from from 1 to 2. And we decided the scaling factor is 1/2, and then we have to convert the function itself. And I took the 1/2 out. It's supposed to be in here, but I can, because it's a constant in this case, I can't take it out. And then I will have e to the power u over v. And then we integrate from there. And so u is easy to integrate, because then when you're integrating with respect to u, it's e to the power u times the constant coefficient 1 over v, and then you resolve from there. So we're starting over here. When you're taking the integral of e to the power u over v du, then this is going to be e to the power e u over v divided by the constant coefficient, which is 1 over v, and that would be v e to the power u over v, and that's what you get here. You plug in v, and it becomes v e to the power 1, and then you plug in negative v, and you get e to the power v e to the power negative 1. And then from there, again, this entire thing is a constant, and so you pull it out and you integrate. Basically, you integrate 1/2 integral 1 to 2 v dv times e minus e to the power negative 1, and then that's the final answer.